Sir, shall we start, sir?
Yes, sir, I'm ready to start.
Yes, sir. Thank you so much, sir. I think it's we are given in YouTube live also. So definitely, I think good evening to all, including our students from various colleges. So for our speaker of the day, our Raman sir has joined. Sir, I think there are finalist people have joined from various colleges, especially the final year chemical engineering students. Very
Very good.
important. I think this Corona, I think, would have given a lots of lesson learned, and definitely now this software tool is going to play a very big role in all the industry, and not nevertheless in the chemical industry also. So definitely your today presence has given us a very heartful welcome, sir, from Institute of Engineers as well as from URSAGO Solution. Definitely, I think the students will know the dynamic, the simulations, especially in the chemical process industry, because they will be knowing only like Aspen or ISIS or something like which was developed in the very prior earliest before. But as our Sims Info system has made so many products, and which is also lying up with various process industry, definitely today's sessions will make them to undergo the dynamic studies. So before we start, let me introduce our speaker in a very short profile. Our today's speaker, our Vaidyanathan Raman, who is the director and CEO of Sim Info System Private Limited. He is also a techno-dominant expert of 35 years in the petroleum, refinery, petrochemical plant. Also, he was worked in a petrol power plant, gas plant, and fertilizer plant. And he has contributed various module development, especially in the dynamic simulations for various chemical engineering sector. And also, I think he has given a lots of lectures for young people who's almost like a completed, like graduating as a chemical engineer. Definitely, today's session is going to be one of the best one we can say that from our Raman sir. Thank you so much, sir, for joining and spending your time in the evening of today. The session is over to you, sir. I think you can start, sir. Thank you so much.
Thank you, Sir Gokul, and thank you for a very good introduction. And good evening to all of you. So let me just start this presentation. We'll have two sections. One will be, I will be explaining about the concept of simulation and how it is useful for the industry. Second is I will also demonstrate a small simulation model so that it will relate to whatever I have said in the first section. Okay. If you have any doubts, of course, you can always raise it at any moment. I have no problem in answering. Okay. Now, our topic is going to be the application of dynamic simulation for chemical process industries. We call CPI. Basically, chemical process industries are, you already know from the word, process industry, which include a lot of industries involving extraction of raw material, their transport, and the transformation into various valuable products by means of physical, mechanical, or chemical processes using different technologies. The examples are many: oil exploration companies, gas oil separation plant, refineries, fertilizers, petrochemical industries, chemical industries, LNG liquefaction plant, LNG storage terminal, paper pulp, cement. You can give many examples which fall into this continuous chemical process industry category. There are other industries like BHEL, UC, SAIL. They are more of mechanical type of industry. Automobile industry, they are more of mechanical type of industry. Primarily, this chemical process industry is almost continuous in nature. So even power plant and nuclear power plant will follow almost in the same category, where you have continuous processing of the feedstock to useful products. So our topic will be towards this chemical process industry. This type of chemical process industry have a lot of challenges and opportunity. So they have a challenge. They must improve productivity to remain competitive. This is true for any industry, but very, very specifically for chemical process industry, because they have very little control over the cost of feed and the price of products. Both they don't have a control. For example, if it is a refinery, they have to buy the crude oil, whomever is supplying crude oil. They don't have any control on the price. And the product prices are determined either by government or by market, like diesel, petrol, and so on. So they don't have control either with the product or feedstock. Similarly, the only thing the only thing the industry can do is control the efficiency of the processing plant. They have to operate the plant efficiently and make money out of it. So the reduction in production cost will go to the profit. So they don't have any other option. They have to reduce the plant operating cost and increase efficiency. And the constraints are many. One of the major constraints is safety. Especially, as you know, continuous process industry have high temperature reactors, furnaces, high pressure compressors. So they deal with a lot of hazard chemicals, so which are very poisonous or explosive. So the safety is a huge concern in any chemical process industry. And environmental regulation. So obviously, like a refinery or a fertilizer or any such plant, you will see always, and chemical plant, you see always there are leakages, there are water effluent going to water, and so on. So polluting the atmosphere, polluting the water bodies will be a major concern. So there are regulation towards it. So they have all these constraints: safety constraint, environmental constraint. They don't have hold on the product feed or product prices, but they have to still make money and run the business profitably. Only way to do that is have a good control over the plant that you are running, run it very efficiently and safely. That's the only way we can make profit out of the plant. Now, the challenge with this kind of plant, the management of this kind of chemical process industry are multiple. So the chemical plants are becoming more and more complex, especially because of the technology advancements. Basic technology advancements like catalyst development and plant design is improving day by day. Besides that, the automation, as you know, automation has tremendously grown over a period of time due to the advent of computer technology. Now, automation is quite directly related to computer advancements. So because of the advancements in computer technology, automation has become very, very complex now. As you know, even home appliances, which we use earlier days, like say washing machine, what you buy, use it 10 years back and today it's quite different. There are more options now, more sophistications, and more trip system are involved in home appliances also. So in a big plant or a chemical process industry, the complexity due to automation and safety system has become very, very high. Because of that, the plant has become more complex. This is one big challenge. The companies bring also new processes and new technologies, products to the market very, very quickly. The changes are very rapid today. Now, if you don't change yourself, you become obsolete and you are out of the market. So you have to keep yourself upgrading all the time and also produce new products as per the demand of the market. So this is the current situation. Again, industrial accident, no more accepted. Accidents ruin your profit, but also image of the company. Not only that, today, if you have any accident, your company shut permanently also. So they not only cause loss to the enterprise, but also the neighborhood and environment. So you cannot afford an accident or safety issue in the today's plant. Earlier days, it was possible, you can still run with that, but today everybody is aware of it. Public awareness is high. Regulations and safety norms are very high and tight. So you cannot take any leverage. And other big concern today is attrition. Attritions are very big concern in every industry, and so is in chemical process industry. People don't stay in the industry for a long time. Earlier days, they join a company and retire from the company. Today, 4 or 5 years is a typical period. Above that, they keep leaving the company for whatever be the reason, and aging factor. So this is again a big problem, because as you know, when some experienced person leaves the company, again you have to recruit and train the person to operate the plant. So this becomes a continuous challenge for the chemical process industry. And as you know, skill comes only with experience. But if you were to replace experienced person who has left the company, again, it requires a lot of effort and time. So this is a big, big concern for us. And one more thing is engineers and managers must respond to changing conditions while onboarding new generations of engineers. Cultural change is also there today. Not only attrition, but cultural change. So with all these constraints, the companies still have to make a money. So this is a big challenge to the industry. And obviously, when there are challenges, you have also an opportunity. So let us see what can be done on this kind. So here really comes the analytical capability, analytical techniques like simulation, where it can be very much used to address many such challenges and problems and issues that you face in a chemical process industry. So our topic will be about simulation. Okay, now let me just define what is a simulation. You might already know about it, but just to sake of continuity. So simulation is basically a imitation of the real world, real equipment or a real plant. That is called simulation. So it's basically used to design, develop, analyze, and optimize technical processes such as chemical plant processes, environmental systems, power stations, and so on. So it has got a lot of applications. It is similar to, I would say, a simple example for simulation is video game. All of us are familiar with the video game, motorbike, car. We keep playing all the time. So it's basically a simulation of the real equipment. It's not actual plane, actual car, or actual motorbike. It's just a software which replicates some behavior of that particular process. That's all. But it's very interesting and useful either for entertainment or education. So if it is a flight simulator, it has got a lot of value because you can teach the pilots how to operate the plane properly, how to start, take off, how to land emergency, how to handle emergency. So it has got a lot of value. If it is a video game, it's entertainment value. So it is not exactly the plant or the car or the motorbike. It is just a simple representation of that particular equipment in a simplified manner. But still, it is quite useful to us. But in our context, the simulation model is same. It is only the software which represents a particular plant or a process. So that is basically the simulation model. We will define more detail about the simulation model in the subsequent slide. So we can categorize simulation into three types mainly. First type is called steady state simulation, where basically we describe a process through flow diagram. So earlier page you would have seen a flow diagram. So of two distillation columns are there. There is a flow diagram. So basically simulation model, steady state simulation model describe this flow diagram where unit operation is like a distillation column is a unit operation, pump is a unit operation, heat exchanger is a unit operation. They are positioned and connected by product or streams. Streams are pipelines. So if you see here, the two equipments, there are multiple equipment. There is the distillation column. There are heat exchangers. Again, there is a distillation column. Then there is a reboiler. There is a accumulator in the top and so on. And all these are streams which are connecting the various equipment. Basically, steady state simulation is a representation of this situation. And this simulation is ultimately a software which is solving the mass and energy balance coupled with the phase equilibrium and transport and chemical reaction kinetics of a system. That's basically the simulation model. We will see a little more detail about this mass balance and all that in our next slide. So steady state simulation, you would already be knowing the names Aspen, HYSYS. Some of you would have already used in your college or you would have heard about this terminology. There are other software like ChemCAD, DWSim. There are many simulation software, steady state simulation software widely used in the market by industry as well as by academic institutes. Okay, now again, this steady state simulation has got a lot of applications, but it's not everything. Some steady state simulation has some limitations, and therefore we need better methodology of simulation. So therefore we call dynamic simulation. So dynamic simulation is an extension of steady state simulator where it is an advanced activity that integrates the same environment, design, operation, and control. Basically, benefits include predicting design limitations over a wide range of operating envelope, overall validation and design performance and capability of safety system. Basically, dynamic simulation, as a name suggests, it's dynamic in nature. Steady state, name suggests it is steady in nature. That means basically the steady state simulation will give result when the system becomes steady. Like for example, if I have a distillation column, I put some feed into it, I'll get product. But this product you will not get instantaneously. It will take quite long time. It has to fill up all the trays in the distillation column. Finally, it has to come out as a top product and product. It will take time. So time is a very, very important aspect. But in steady state simulation, the simulation is done such a way, once the system becomes steady, finally what is the result? The final result is what is shown in steady state simulation. Whereas in dynamic simulation, it will simulate the condition of the plant or a process or an equipment as a function of time. So it will tell you every instant how the parameters are showing. So when I put a feed into the system, how the temperature is changing, how level is changing, how the product is coming over a period of time. That is dynamic simulation. So the main difference between steady state and dynamic is dynamic simulation includes the time aspect, whereas steady state simulation will not bother about time aspect. It is the final result which will be used in the steady state simulation. Therefore, it will become a simpler model. Dynamic simulation, because of the time aspect, it is more complex. There are many simulation tools like Aspen, HiSys, Unisim, DynSim, MATLAB, Apros, and so on. There are many commercially available steady state dynamic simulation software available in the market. We have put one, our product is called Pro Simulator. It is also a dynamic simulation, and I'll demonstrate that now in the next section of this presentation. The third category is called training simulator. Training simulator is also a dynamic simulation, but it has got some more component to it. I will demonstrate mainly a training simulator and explain the main component in the training simulator. Okay, now if you take a plant, you go to a refinery or a gas plant or a fertilizer plant, there are many things, many activities happening in the plant. Now, when I want to construct a new refinery or a new fertilizer plant or a new LNG plant, anything I want to construct new, initially you have to design. That's the first activity. In design, there are two stages of, in fact, there are multiple stages, 3 stages of design. First stage is conceptual design. Suppose I want to build a new refinery. Today, CPCL refinery is going to build a new refinery at Nagapatnam, 3 million ton, I think 6 million ton refinery. Now, right now it is at conceptual stage. Conceptual stage means I know what products are demanded by my market, and I will know what crude I'm going to process. Now I have to come out with overall configuration of the refinery. Okay, what are the plant I will have in my refinery? What is the capacity of each plant that I will have in my refinery? That is the overall conceptual design I have to first do. This conceptual design will be first step, where you find the optimal design through fast evaluation of design alternatives with flexible specification and continuous solving. Say, based on the product demand and feed availability, this conceptual design will be done. If I am designing a refinery at a very cold region, let's say Kashmir, I'm putting a new refinery, the design will be different. If I'm putting in a very hot place, maybe Chennai, the design will be different. So based on the ambient temperature, available of raw material, feedstock, and product demand, this conceptual design will be, broad design will be done by the licensor, the technology licensors. Next stage is called feed, where front-end design. Here, we will do more detailed work. Okay, taking this conceptual design as an input, we will do more detail about every plant. Like a refinery has got many plant. It has got a crude distillation unit. It will have an FCC. It has got hydrotreaters. It has got an hydrogen plant. If you go to any refinery, there are many plant involved in the refinery. So we will have to design each of the plant. What is the capacity? What are the how many trays will be there in my distillation column? The reboiler capacity. So I will be doing the major sizing of the equipment. I will also be determining the capacity of the every plant which I'm going to have it in my complex. So this will have more detail step. The next stage will be detailed designing. Detailed designing is, okay, there are hundreds of pumps will be in the refinery. There are many heat exchangers will be there. There'll be many furnaces will be there. Now, each equipment will be manufactured by different vendor. Okay, one vendor will not supply everything. There are vendors who will supply only control valve. Vendors will supply only pump. There are other vendors who will supply heat exchangers and so on. So we will have to give detailed specification to each vendor for that particular equipment and make sure they design it properly and give it back so that I can put it and build my plant. So this is done at detail engineering stage. And so this is the third step involved in building a plant. So here also I will design all my instrumentation, control system, safety system. Everything will be designed during this feed stage and detail engineering stage. So once I design my plant and commission my plant is running now. It's already commissioned. Everything is done. And I'm producing product. After that, so you will have to, okay, once my plant is commissioned, I have to do startup of the plant. Startup is very important activity, first time especially, because your first time trying to create a product out of the plant which is designed based on a lot of assumptions, based on a lot of vendors, based on a lot of calculation. Anything can go wrong. You might have made mistakes in some steps. Your assumptions might be changed and so on. So during startup, you will have to make sure that all the problems are solved and you commission the plant and you get product out of your plant properly as per your initial expectation. So if there are issues, you troubleshoot and solve the problem along with the designer. So this is a very important step activity where we do the startup properly and bring the plant online on stream. So this is a very important commissioning and installation of the plant. Once it's all done, you are running the plant, then comes the operations. So once my plant is running, I have to regularly operate the plant round the clock, 24 hours, 365 days, I have to run the plant. Now, this is the responsibility of the operation department, where they have to keep on monitoring the parameters on a continuous manner, and they have to make changes, and they have to do the production as per the market requirement and other constraints they are facing day to day. So this is the operation work. And here, when I'm doing operations, I also have to see whether I can do any improvement. If I am finding some problem, whether I can debottleneck my plant, whether I can increase the throughput, and so on. So here, this operation. So this is the operation step. So basically, therefore, there are multiple steps involved in any plant, and this is the full life cycle of starting from conceptual design to detail engineering design to startup and running the plant properly, doing online debottlenecking and optimization of the plant parameters is a full life cycle of the plant. So basically, the dynamic simulation we will talk about is called, basically it's a multi-period dynamic simulator, and we use a simulator for all these aspects of the plant requirement. We use a steady state simulation for doing conceptual design and feed. Then we use the dynamic simulator for detail engineering, startup, and operation improvements. This is how we apply. So I will just go to the next slide. Okay, now this simulation model is going to be built based on the fundamental principles of engineering you are taught in the college, like heat balance, mass balance, reaction kinetics, phase equilibrium. Now, any equipment you take heat exchanger, for example. All of us are aware that if you have heat exchanger has got two sides. One is hot side and cold side. First, material balance is very important. Hot side, whatever I'm putting inside should come out, the material should balance. Similarly, cold side, whatever input is going to be output. And that is the mass balance. Heat balance will be the hot side heat balance should become balanced with the cold side. So you have equations like MCP delta T equal to Q equal to UA delta T. So that is basically the heat and mass balance for a heat exchanger. Suppose I got a distillation column, then I have trays. In each tray, you have got vaporization happening. The liquid we are putting inside will become partly vapor and partly liquid. So I have a phase equilibrium between vapor and liquid. So I need to calculate how much will become vapor, how much will become liquid, what is the vapor composition, what is the liquid composition. So this is vapor liquid equilibrium calculation, and that is part of mass transfer calculation, which has to be done wherever there are phase changes. Suppose you have got reactors, then reaction kinetics have to be applied, and you have to use the reaction kinetics thermodynamics laws and model the situation. So basically, these four, mass balance, heat balance, reaction kinetics, phase equilibrium, will be the governing principle for modeling any equipment or a plant. Now, if it is a dynamic simulator, we have got one more complexity called momentum balance, which is nothing but pressure balance. In a plant, as you know, there are a lot of rotating equipment, like pump is a rotating equipment, compressor is a rotating equipment, where fluid is moved from one place to another place through the pipeline by increasing the pressure of the fluid by either pump or compressor. If it is vapor, it is compressor, gas or compressor. If it is liquid, it is pump is used. So this will increase the pressure. So when there is a pressure increase, flow will increase. So pressure and flow has to balance properly. That is called momentum balance. So this basically brings the dynamics in the real plant. So you got 5 main principles: heat balance, mass balance, reaction kinetics, phase equilibrium, and momentum balance. These 5 basic principles will be applied for any equipment, and simulation model will be built. And all these 5 equation is what you study in your college, as in terms of heat transfer, mass transfer, reaction kinetics, thermodynamics, transport phenomena. That is exactly what is taught to you during the first 3 years or 4 years of your chemical engineering degree. So that is what is applied in simulation also. So we write the equation for every equipment, and this equation is called simulation model. These equations will be converted as a software, and that is called simulation model. Only one thing is, as I said, if it is a dynamic simulation, the temperature, but time will be an important factor. So I should be able to calculate rate of change of temperature with respect to time, rate of change of hold up with respect to time, and so on. If it is steady state, I won't bother about time. If it is dynamic, I will bother about time. Therefore, my equation will become more complex because I will have differential equation which has to be incorporated in my simulation model. I have to solve differential equation as part of the solution. Okay, so it becomes a little more complex. However, nowadays with the good computing capacity and capability, we are able to solve even high degree of differential equation in real time. So then we will have a lot of instrumentation in the plant. As I said, instrumentations are very much important because a plant is very huge and you need to know at different locations in the plant, what is the temperature, what is the flow in the pipeline, what is the composition, how much is the level at different locations. All this you continuously require to monitor. Okay, if it is a simple pump in the household, you don't show anything. You don't even have a lever measurement. You will go up to the overhead tank and just peep through the opening and see how much is the level. You don't even have an indicator there. Whereas you cannot do that in a plant where there are hundreds of equipment and the plant is scattered over kilometers. You cannot just simply watch and see what is the level. Similarly, you do not know what is the flow, you cannot operate. So in order to make your job easier and practical, lot of instrumentation is implemented in the plant, like level gauge, temperature gauges, flow measurements, and so on. And these measurements are transmitted to a convenient place called a control room. It is to why the measurement is done, and through the signal is transferred to the control room. Today digitally it is transferred. So in control room you have computers on which you can monitor what is the temperature at this particular distillation column, what is the pressure in the downstream of the pump, what is the flow through this pipeline. All these parameters you can monitor in real time sitting from a computer in the control room very conveniently. So, and not only monitor, but also I can make changes. Suppose I want to change the flow rate in a distillation column, or I want to change the temperature. I can always go and change the temperature. I can change the flow. I can change the pressure remotely sitting from the control room automatically, thanks to the advancement of instrumentation and automatic process control. So today the technology has advanced that if I just give instead of 100 cubic meter, I want to raise it to 120 cubic meter per hour. I just simply give a simple command in my computer. Automatically, the process control system, there is a PID control, proportional integral derivative control system, PID control system, microprocessor based control system is available in the plant. And this will automatically take your input, and it will find the difference between the current value and your desired value. Based on the error, it will calculate how much valve should be increased or decreased. So this information will go to the valve. There is an air regulator. The air will be sent to the diaphragm of the valve, and more air will be supplied. Because more air is supplied, valve opening will increase. If valve opening increases, conductivity will increase, flow will increase. So this kind of automatic control system has come in the plant, real plant, which is enabling us to operate the plant remotely. So this is the instrumentation part. The last one and most important is safety system, emergency shutdown system, and trip logic. It's very, very critical. As you know, I was telling about home appliances. You even just take a washing machine. Today, there are many trip systems. If suppose you find suddenly there is a vibration, immediately that washing machine will trip to safeguard the system, safeguard the equipment. Similarly, if there is high current coming, the fuse will go off in our household electrical system in order to safeguard the equipment. Otherwise, you will have damage in the equipment. So there are safety, therefore, in every equipment implemented in the plant. Because plant has got hundreds of equipment, this trip logic system is very complex in the real plant. But all this has to be considered in our simulation so that it will replicate the real plant in a meaningful manner. So when I do all these equations, I will have a lot of equation to be solved in the computer. And this will be solved numerically. You would have studied numerical mathematics during first and second year of your curriculum. You would have, so there are many methods to solve. So we'll use numerical mathematics and solve these equations. And the results will basically be the parameters which you will be interested: flows, temperature, pressure, level, composition. And these values will be computed on a continuous manner. In a dynamic simulation, plant is continuous. It is not like it will, once you give the feed, it will solve and then it will stop. It is not like that. It is continuous process. So there are batch industries also, but primarily any continuous process runs 24 hours, 365 days. So simulation model also will run continuously. So what I will do, I'll solve the equation and get the result and show the result to you. Again, I will solve the equation show the result, and again. So I'll keep on doing this in a continuous manner so that I do exactly like what this plant is doing. Now, say every second or every 500 millisecond, I will do this computation on a continuous manner. And these parameters that I'm calculating will be displayed to you in a very convenient manner. That is very important. So depending on your application of the simulator, what for you are using, the results will be displayed properly. Suppose I'm going to design my plant, or I'm going to do validation. You would have used Aspen or ISIS maybe, or the results will be shown to you in tabular column primarily, Excel file or tabular column. Suppose you define the feed and you give all the specification, run the simulation, it will solve and give you the result in a tabular form or Excel format. So you can see what is the top product purity, what is the top product flow rate, and what are the temperature in the column. All these parameters you can see tabular column and an Excel file elegantly today. But suppose I'm going to use it for, let us say, training somebody on plant operation. I cannot show in a tabular column. He will get crazy. He need to see that parameters in the same way as he is looking at it in the control room. Control room, how he will see the plant, the same way you should display the parameters to him. In my next presentation, I will show how control room will look like, and you will see how it will be realistic like a real plant. Like, video game. Suppose you are playing a video game, the displays are very important. When you are raising the speed or you are changing the direction, you will have panels which will show as if you are really seeing the panel of the real equipment. If you are driving a car, whatever you are seeing, it will show you distance travel, it will show you the left side mirror, right side mirror, all this will show you, so that you will feel as if you are actually running a car. That realistic feeling will come to you. The same way, in the simulation also, the display has to be like what you are seeing it in the real plant control room. Okay. Now there are extra, that is what we call DCS. DCS stands for Distributed Control System, which is located in the control room, which monitors all the parameters of the plant, and it displays to you on a real-time basis. It also allows you to make changes in the plant parameters remotely. So that is called DCS, Distributed Control System. Any modern plant today has a centralized control room with DCS. Basically, DCS is a computer system, okay, where operator and engineer will sit and operate the plant, monitor and operate the plant on a continuous basis. In the simulation, you also have to take care about external disturbances and instructor. This I will talk a little later. Okay. Now this dynamic simulation has got a lot of application. Can be used for evaluation of new process concept, safety analysis, integrated plants control design, development of new control strategy, automation testing, then automation engineering, performance analysis, training operators and engineers, troubleshooting, optimization. So dynamic simulation is used in many applications in the actual plant in today's world, especially because of the good computing power availability and advancements in technology. Today's dynamic simulators has got tremendous applications in the real plant. And steady state simulation is also used widely. Both steady state and dynamic simulations are used. This particular slide shows where what is used, steady state versus dynamic simulator. So during conceptual design, steady state, SS stands for steady state simulation. Detail engineered process design, both steady state and dynamic simulation is used. Control design testing, dynamic simulation. So if you want to do any modification, both steady state and dynamic is used. Automation modification, dynamic simulator. Safety analysis, troubleshooting analysis, dynamic simulator. Any optimization you want to do in the plant, both simulators are used. For training, dynamic simulators are used. So basically, both simulators, steady state and dynamic, are very useful, and which will have, and together they cover all the requirement of the process industry. That's why we call full life cycle, multi-period, multi-purpose dynamic simulator. Basically, if I combine steady state and dynamic simulator, it is called multi-purpose dynamic simulator. It covers all the life cycle throughout the plant. So this is just pictorial representation of simulation. So this is a real plant. This plant could be a power plant, refinery, or a gas plant, any continuous process industry where all the equipments are connected. There are many equipment like distillation, reactors, furnace, compressors, pumps, heat exchangers. So many equipments are there in the plant. All these equipments are connected by pipeline, and you are putting some feed and making some products out of it. Lot of streams. There are vapor stream, gases, liquids, steam. All these are available in the pipeline. Now, the plant is very huge. It may be few square kilometers spread. Now, therefore, as I said, a lot of instrumentation is deployed in the plant. You will measure all the required parameters, putting sensors at the pipelines and equipment, and collect all this data and bring it to the control room. In the control room, I'll have wiring from the plant to the control room. And in the control room, I have special computers we call DCS, Distributed Control System. And in the control room computers, I can monitor the plant in a continuous basis. And I can also operate the plant from these particular computers. This is how the real world is. And in the simulation, what we are doing is this real plant, which is physical, we will model it mathematically by the principles of engineering of every equipment, convert it as a software, and run this software in the computer on a continuous basis. So this simulation model running in the computer represent the plant in a dynamic manner. And in the like a control room, I will also provide the same display for the user so that user can see as if he's operating the real plant, but actually he's not operating the real plant. He's operating the simulation model of the plant. So it is almost like operating the plant we call virtual plant. So this is what we are doing as a virtual plant. So there are photos of some of our client where simulation is being deployed. Say this is a control room where they are operating the simulation plant. This control room of the actual plant also is looking similar, and exactly the same manner here also in simulator also is there. There are another client which is using in simulator in Turkey. This is the Rashtriya Chemical Fertilizers in Mumbai. And here this is a refinery in Bathinda, Punjab, HMEL refinery where simulators are being used. This is a client in Saudi Arabia, a petrochemical industry where simulation is used for some studies. This is in Oman, Petroleum Development Oman, PDO, gas plant. So different people are using simulators for either training their operators and engineers or doing any studies or troubleshooting or improvement and various applications. In today's world, simulations is used in a very useful manner. So this is just a first presentation section, and I will go to the demonstration. But if there are any questions, of course, I can take it up and answer you also. Meanwhile, I will just load the simulation model. Please tell me whether you are able to see my new screen.
Yes, sir.
Okay. Now, I will take an example. If there is any question, you can also ask me anytime, but I will continue because time is also not much. How much time more I have, sir?
No, sir, you can take up your own session. No issues. Maybe.
No, but they should not feel sleepy. So I should stop at right time. That's important. Okay. Now, this is a demonstration I'm going to make of a simulation model. One of the example we have developed. Okay. Now, what happened is in our simulator, there are two components. One is instructor component and trainee component. Now, both are software only. Now, I can select the simulation model which I want to train or demonstrate the user. For example, I can say in a refinery, I want to train the person on crude distillation unit. I select the crude distillation unit model and load the model. Once I load the model will get loaded. The simulation model will get loaded. This model means software will get loaded. Now it is running in the background to calculate all the parameters of the crude distillation unit. Now, as a user or I am a trainee, let us say I am an engineer operating the plant. I want to operate this simulator and learn the operation of the crude distillation unit. How do I do that? So here I have another screen. This screen will be like a control room screen. If you go to a control room in a refinery, people who have gone to any process industry, fertilizer, gas plant, refinery, any place you've gone, if you have visited a control room, it will look like this. So this is a crude distillation unit. And in this crude distillation unit, there are various sections. Different sections are represented graphically in different pages. So I can go from one page to another page through, I can just keep on changing my page. And now I'm going to see the furnace, crude furnace. Here I have, this is the furnace equipment, and I have pipelines. See, this is a feed to the furnace, yellow color line. This is a crude oil coming through the furnace. And then this crude oil getting heated. Furnace objective or the purpose of the furnace is to heat up. So what I'm going to do, I'm put the fuel from the bottom. There are burners here. I'm putting fuel from the bottom and also air, and I'm burning the fuel. Because I'm burning the fuel, the crude oil which is passing through the tubes will get heated and temperature will be raised. That is the purpose of the furnace. And how much temperature is raised, you see here, I am measuring various parameters. I'm showing the temperature here. The temperature, if I click this, if I click any of these parameters which is showed in a box, it is now 360 degrees centigrade. The temperature of the furnace is 360, but the feed temperature, what is coming inside is 247. 247 degrees centigrade, it is coming inside. I am raising the temperature to 360 degrees centigrade by basically putting fuel and air in the burner and burning it and raising the temperature. Similarly, I can see another page. This is the feed first page. I'm taking the crude oil from storage tank and there is a pump here. This pump, because crude oil storage tank is far off, I'm having a pump which will raise the pressure because the plant is located maybe some 2 kilometers away. I cannot how to move this crude oil from tank to the plant. So I use a pump, raise the pressure, and then send the crude oil to the plant. The plant has got various heat exchangers where the crude oil will get heated. Then it has got an equipment called desalter to remove the salt. Then it will be again the pump pressure. The pump will raise the pressure to higher pressure, and then it will go to further heating through various heat exchangers. Then it will go to furnace where by temperature will be raised. Then it will go to a distillation column where basically my crude oil will get heated crude oil. Heated crude oil will get separated into various products. As you know, in refinery, crude distillation column will separate the crude oil. Crude oil has got many components in it. It has got LPG, it has got gas, it has got petrol, it has got kerosene, diesel. So many products are in the crude oil. But I cannot use crude oil as it is. My demand is for LPG, my demand is for petrol, for diesel, for kerosene. I want different products. So this distillation column will be used to separate all these products and then sell it in more valuable product. So this is a distillation column. So here, if you see, a lot of parameters are displayed for you. Temperature in the distillation column. Then it shows what is the level in the bottom of the column. So I can click any parameter or every parameter is shown to you dynamically. You also watch closely. These parameters will be continuously changing. Small changes will always be appearing. Say it is now 51.24, 51.21. Slowly it is changing. So like a plant also, nothing will be so steady. There will be always small changes all the time happening. So I can go and make any change. Suppose I want to change the flow rate of some particular fluid. For example, I want to go to change the top temperature. It is now 125 degree is the current value. Suppose I want to change it to 120 degree. I go and change from control room. I say 120 degree. If I change to 120 degree, see there is a PID proportional integral derivative. This is a controller. Process control you would have studied. So there is a PID controller. This is a microprocessor PID controller. Now this based on the error which is between the actual value and the current required value, it will calculate the output, and this output will regulate my flow to the column, reflex flow to the column. If you see these two are connected, this temperature is connected to the flow rate of the reflex. Reflex flow will be regulated so that temperature will come down automatically. If I increase the reflex flow, the column will get cooled. The temperature from 125 will come to 120. Slowly it is coming. Now, as I said, the changes will happen slowly because that is a real situation. There are a lot of hold up in the equipment. The plant capacity is very huge. So if I change some parameter, it won't instantaneously change. It will take some time. Like you use iron box in the house, you change the setting, suddenly the temperature will not change. Gradually it will change. Iron box is a small equipment, so maybe within few minutes you will require the required temperature will attain. But this being a huge equipment, it will take quite a long time. It may take even sometime half an hour to, based on the change that you are given, it will take longer time. This is a transient behavior. That is the behavior of the plant parameter as a function of time. That is what this is. So any change I make, the changes happening in the, now what will happen? The changes will not only happen to this particular parameter, but it will also affect other parameters, right? I was interested in only changing the temperature. Fine, that is changing, but it will also reflect the changes in other temperatures, other level. Every parameter will get affected. See, the bottom level has gone to 57. It was 51% earlier. Now it has gone 57 because I changed the top temperature. So any change I make, will have automatically influence on all other parameters because they're all connected and they work together. And this change, this all calculation is based on the fundamental principles of engineering. That's how it is all calculated. But you will see as if it is happening in the real plant. In the real plant also, from control room, if I operate and move change, it will appear exactly like this only. So now I can also see how I can go to another screen where I can see how the changes are happening. So this is the, we call trend page. Earlier what we saw was a graphics page. Graphically, I represent the plant. Here I am showing trend. Trend means x-axis is the time axis. You see here, this is the time axis. 416, 417, 5. So the time axis is in the x-axis. Y-axis are different parameters. So I can plot, like you do any experiment, you do plot in the lab, no? Same way you can plot here and see how the changes are happening. If I make one change in one parameter, how other parameters are behaving. Different parameters are shown in different color. So I can see how the parameters are interacting with each other as a function of time. Now I can make small change or big change. For example, I made a temperature change. I can also make a huge change. For example, from the instructor, I can give malfunction. I can say suddenly, say failure of some equipment. Say I say booster pump failure. This is a very important pump. If I fail this pump, see this is the pump I'm failing. I stop this pump. Because I stop this pump, crude oil will not be flowing now. The crude oil flow will go to zero to the furnace. If crude oil flow becomes zero, you will see the temperature of the furnace will shoot up. It's gone to 400 degrees and it's gone into red. And you will have a lot of alarms coming now. So many alarms will be coming. In fact, you will also have a buzzer sound, and it's not now sounding because it will disturb. So otherwise, you will have a lot of buzzers coming in. It will create a lot of, because I stopped the crude oil flow. Because I stopped the crude oil flow, the temperature has gone very high in my furnace. All the parameters will get terribly upset and the plant will totally go into an extreme condition. So I can make small change or big change and simulate various conditions and understand the plant behavior very realistically and safely. I cannot do the same thing in the real plant. I cannot stop the pump which is supplying the crude oil to the plant and watch up what is happening in the plant. If I do that, I'll be kicked out of the company because you are going to trip the plant. But in simulator, I can do whatever I like, and I'll be able to see how they are related, how they are correlated to one another, and I'll be able to understand the behavior, dynamic behavior of the plant in a very right manner. So I can do analysis and then I can make a lot of benefit from that. And so this is the main way it can benefit the operators, engineers, designers, how to study, understand the behavior of the plant and dynamics of the behavior of the plant, and how the safety system is working. All that they can understand very clearly using this simulator. Now I made a big change, so plant is upset. I can just reset and bring the plant into normal condition again. And this being a simulation tool, I can reset like a cassette recorder. No, I can just reset and bring it to normal condition again. See, now everything is normal. So I can always go back to the normal value anytime I like. And now I can make the next change. I can make such experiment. So because you make one change, the plant is entirely upset. If I make another change, you will not know which is causing what. In order to understand properly, one by one, you can make a change, get back to the old value and make the change again. So I can really use it as a good tool to learn the dynamics of the plant in a very realistic manner and a safe. What happens in the normally when you go to a plant, like you join a plant after your graduation, you need to go through maybe years of training, and then only you understand and slowly get the grip of the plant, and then you will be able to operate the plant. Whereas you don't today have such time. As I said in the initial presentation, attritions are a big concern. Today, people are not staying much. You cannot spend many years of training today. You need to train them in a short period of time very smartly. So the simulator can be extremely useful because what you learn over a period of 1 or 2 years, you can learn within few weeks if you sit on the simulator. So I can suddenly stop this fan. For example, if I stop this fan, one fan is 4 fans are there. One fan I stopped. If I stop the fan, cooling will reduce. Cooling will get affected. Because cooling will get affected, if you see here, my pressure will increase, my temperature will get affected, everything will get affected. So I can see the effect of such disturbance, such problems one by one, understand it very realistically. So, and I will get the same feel of operating the plant from the control room. The feel is very, see what happens is if you're an operator or engineer, you are operating the plant. Not only your theoretical knowledge is important, theoretical knowledge is must, no problem, no doubt. That is the basic fundamental thing which is required. Besides theoretical knowledge, you need to know you need to have the skills, you need to have the confidence, you should have the reflex, you should know the standing operating procedures, you should be able to communicate properly, you should work with others. So many skills are required to be trained. This simulator is a good platform to impart such skill and capability and confidence on the people who are operating the plant in a very short period of time. So this is one big application of the dynamic simulator, which is now becoming a must for all the industries. And everybody who is building a new plant, they are building along with the simulator. Our company, we are located in Chennai. We have about, say, 60, 70 people, engineers, full-time working. Their job is to develop simulators for any new plant coming in the world. It might be coming in Middle East or Africa or Europe, US, wherever new plant is coming, we'll build simulators and we'll supply it along with the plant. So before even plant is ready, they will get trained on simulator. They will use a simulator for verification and all the optimization requirement, and then train everybody so that people can avoid mistakes, because mistakes are not tolerated. And similarly, any safety issues or environmental leaks are not tolerated today. So you can avoid, only way to avoid them is have good people who are trained very well, who are very confident, like aircraft simulator, aircraft industry is there. Pilots are very well trained on a routine manner so that they don't make mistake. You cannot afford pilot's mistake in a plane. You know that complicated implications. Exactly in the same manner in a nuclear power plant or of course, Mr. Gokul is in space industry. Space industry is much more. And refinery or gas plant, anywhere, you cannot afford mistakes today. If you make mistakes, it's a catastrophic to people's life, equipment, cost, profitability, even the sustenance of the company will be questioned after that. So we have to put all the effort and advancements towards avoiding mistakes in design stage, in operator skill, engineer skill, as well as on a continuous basis, you have to improve the operational performance. So dynamic simulation is one of the major tools used in the industry today. And fortunately, in the industry today, there are many companies who are having this kind of activity taking place in India. Almost all the design companies, multinational companies, whether they are automation company or they're a design company, process design company, they're all located now in India in a big way, because India has good engineers and in a cost-effective manner. So they have big companies in Chennai, Bangalore, or Mumbai, or Delhi. They're all located in many such cities, Hyderabad, and they are doing almost all the design. It's Shell, Foster Wheeler, then Technip. There are many Petrofac. There are many companies who are all located in India now, and they are doing design for all the world requirement, not only Indian requirement, worldwide requirement. They are doing from India. So that's a big advantage to all the people who are graduating. The job potential is enormous in this particular. So if you have your basics very strong, your what is taught in the college, and if you are able to use your computing capability to do simulation, you have great amount of job opportunities available for you in the coming years. That's a big advantage today. And with that, I would like to take any questions if you have, so that I can answer them and add to whatever I said already.
Yes, sir. Thank you so much, sir. I think definitely, I think you have given a very nice presentation, and also like the importance of the simulation, because I think making some theoretical and working out in the classroom session, I think that will not like fetch out when they step inside any industries. So definitely, I think your session have given them a practical experience, and also before they go to any kind of a PLC board, today they have seen how this each and every parameters play a very important role. And as you said, I think no company will afford it to do any kind of simulations during the running plan. So they have to do it in the back end. That is what I think Sim Infosystem is doing a lot. So definitely, thank you so much, sir, for joining in the evening session. And you are on the dot. Actually, we started at I think 17:03 and we ended up at 17:58. So that itself shows the importance of time. So thank you so much, sir, from the IEI, TVLC, as well as URSAGO Solution. Dear interns, I think we are opening up for the QA session. So you can maybe unmute yourself and you can ask the queries to the sir. If at all, otherwise you can even drop in the chat box also. Who is like the first one? Any like people who can ask query?
Hello, sir.
Yes.
Sir, this is Muthu from Agni College of Technology. I'm a final year student, and I have a very simple doubt. So it's you have said that you're having chemical engineers around 50 to 60 people who are working and designing these simulation softwares. Can you please explain the process that is used for the simulation software designing in a short way?
Yeah, basically what we do is we have two type of solution. We have our own simulator, we indigenously developed, owned by our company. That's called Pro Simulator. So we also have expertise in using any other simulator like Aspen or ISIS or Unisim, many other commercially available software also. Based on the project requirement, we use appropriate software. The first step is to collect data from the plant, understand the plant properly. That's the first step. We take their PNID, PFD, understand the plant, and collect all the data sheets. There are a lot of information required from the client, and we have a kickoff meeting to start the project. During the kickoff meeting, we will explain how the project will be executed, what data is required, and when the data is required. So the client will have to put a lot of effort, give all the data to us. We analyze the data, understand the plan. Then next step will be to develop a specification for our job. So first of all, we develop what we call functional design specification. This document will take about 1 or 2 months time based on the size of the work. This will detail all the scope of the simulation that we are going to do, what are the boundaries, what assumptions are made, what malfunctions will be simulated. This document will be developed and submitted to client for their comment and approval. After that is approved, we'll do the simulation model development. Every equipment we will take and we will model them based on the principles of engineering behind that. We will write the equations and then do the conversion of the equation to software. If the equation is, for example, heat exchanger pumps, which are already routinely done, we have a library which we can just simply use it. But if it is a new equipment which we are not having in our library, we have to develop the appropriate equation and then develop the code, software code for that, and then make the model. So once we develop all the equations which are required and convert them into software, we have to do a lot of calculation, heat and material balance calculations, and equipment calculation which are required to be supplemented. These calculations will be done, and then we will first of all run the simulation, make sure that we are able to replicate the steady state behavior of the plant, because they have given the heat and material balance data. I will be able to see whether my simulation first of all represent their steady state. After that is checked, then we will do the model dynamic testing. Suppose I change the feed, what happens? If I change this condition, what will happen? I will make dynamic changes and see whether it operates like a real plant. Then I will do startup of the plant. I will do the shutdown, startup, and check whether my plant is working like a real plant. This is the done. After that, I will incorporate all the instrumentation and safety system which is taken from the client, and which will be a very extensive work. After building the instrumentation and safety system, again, we will do the startup, we will check all the malfunction, and then do an internal testing. Then call the client for what we call FAT, factory acceptance testing. Client engineers, client managers will come and they will do extensive testing of the simulation model, and they will give comment. Based on their comment, we will improve the model, and then supply this model to the client, and then install the simulation model, train their engineers how to use the simulator, and then support them as a warranty. So this is a full life cycle of the project. So our engineers involved in starting from kickoff meeting, data collection, model building, do everything till end site support. We'll do all the activities for our clients.
Thank you, sir.
Yeah.
Excuse me, sir.
Yes.
Sir, I am Babin from Sriram Engineering College.
Yeah.
I'm having a doubt, sir.
Yes.
You have said that company will say the freshers to create simulator for industry all over the world. That you said before that company will select some freshers and they will ask them to create simulators. How will the company will select the best simulators from the people?
No, actually,
Professor.
Sir, Raman sir.
If you are an operating company, if you are joining a company like our company, say simulation company, then we will teach you how to develop simulation model. We will give you 2-3 months of training and tell you how to develop simulation model using our tool and software. And then you will be able to develop simulation model on your own. That's how it is done.
Sir, I am asking that company, that
Okay.
manager, how will he select that? How will he select the best from that simulators? Sir?
Sir, Raman sir, I think some network problem with you, I think, sir. You have got hanged. Your voice is not hearable. Maybe Raghuram sir? Okay, maybe 2 minutes. I'll just check up by calling you.
Yeah, thank you, sir.
Hello. I hope I'm audible again.
Yes, sir. Audible,
Yes,
sir.
sir.
Yeah.
It got disconnected.
Now,
Okay. Yeah. So today it's used extensively for such verification purposes. And because of that, what happened? Simulation costs a lot of time, energy, and money to develop. But whatever verification you do in the beginning, it will pay for all this cost very easily. So the very important application is definitely the verification of the design.
Yeah, thank you, sir.
Yeah.
Yeah, thank you, sir.
So we have a few, I think, questions from our chat box also.
Good evening,
Yes.
sir.
Yes, please tell me.
Good evening, sir. I'm Sheetal Chandrasekharan from Satyabama Institute. I'm having this doubt, like we know that AutoCAD is most common among people. Like, will there be a day when these softwares also get common? Like,
See, AutoCAD is common, as you say, for drawing, definitely. It's becoming now simulation would become like that, definitely, because industry, it is becoming very, very part of industry now. Every part of industrial operation, they are using simulation. Definitely, it will become the order of the day, especially like, of course, I know space industry, Ms. Gokul would tell a lot about it. Simulation is must for all that activity they do, because they don't see everything. They have to simulate only and see. So definitely, other process industries also using simulation more extensively. In education segment also, simulator is becoming very, very vital now. It would definitely be the trend in which it will go.
Thank you, sir. Thank you.
Yeah.
Sir, I have another question. Sorry.
When somebody else started, is this all that I want to achieve in life? And I figured out that the increase in...
Yeah, Shadal, you can proceed.
Yeah. Sir, what will be the job title if I work with this software?
No, based on where you join. If you join a company like us, we call you simulation engineer.
Okay.
But based if you go to a refinery, they call GET and then put you as a basic engineer. So based on where you join, right here in simulation company, we call you simulation engineer.
Okay.
Then senior simulation engineer and so on.
Sir, how long does it take to become a senior simulation engineer?
Maybe 3 years, maybe 2 to 3 years.
Okay.
And also depends on your performance.
Absolutely.
Yes.
You may even begin in 6 months if you are very good. So,
sir, like if I'm getting trained in a company, will I be given a posting again, like to train another fresher or something, or like only some person who's expertised in that will give the training?
No, basically, definitely you will also get the opportunity. Once you know how to use the simulation, if you're able to develop the model, you will also become a trainer sometime or other.
Okay, sir. Thank you.
Yeah.
Sir, this is Muthu Mayal. I just have another doubt.
Yeah.
Can I?
Yeah, please.
Yes, sir. So in our college, we were given training from Meridian School of Oil and Gas for about 2 years
Right.
in this software. Is
Yeah.
that training useful in any kind or something while we join a simulation company?
Definitely any training would be valuable, definitely, because simulation is not separate science or anything like that. It is what all you study is basically applied here, that's all. It is not learning software, it is not like any new concept. It is same as heat transfer, mass transfer, and so on. So whatever you learn in the college or extra that you learn would definitely will be useful in any job that you are going for. Definitely it will be relevant only. Of course, if you have some familiarity with some software programming, it will definitely add to your value here. But otherwise, basic knowledge that you have required to be in the college is most important.
Okay, sir. So you were saying that if any new equipment is used during the design process, you will be writing new codes for that. If it's not already present in your library, in which
Correct.
language they are writing these codes, like C, C++, or Java, like that, sir?
In our company, yeah, we are doing Visual C++. Visual C++ is used as a programming language.
So if we apply for a job like junior simulation engineer like that in any design concern, we must be having knowledge on C++ like that, sir.
No, it's useful definitely if you have that.
Is that
Otherwise, you have to
required?
learn. That's all. Once you join, you have to learn. It's no option. You have to learn anyway. But most important, as I said again, your basic engineering, if you are very strong, even if you lack in some computer skills, you can come and pick up. You should not have difficulty in learning. Some people have difficulty in learning software and all that become a problem. You should not have any aversion. But if you know already, it's an advantage. You can get started much faster. That's all.
Okay, sir. Thank you.
Yeah.
So we will go with some queries in the chat box. There are 3 questions
Yes,
in the
sir.
chat box. One is
Yeah.
from Rashika. Sir,
Yeah.
is the simulation used only in the operation process or even in testing the projects before implementing it?
As I said earlier, it is used definitely in the new projects, especially new plant. Before it's commissioned, we use the simulation extensively for testing, validating all the design data as well as operating procedures, which is recommended by the licensor. So very much used for design verification and testing.
Yes, sir. Thank you, sir. Another we have from Magesh. I think he's from Sriram. So the steady state simulation or dynamic simulation, how did they determine this simulation suits for the particular process?
Yeah, as I said, I have given earlier presentation slide, one of them, where steady state is applied, where dynamics applied. So in some, based on the objective that you are, suppose in the beginning, if you are doing a new conceptual design, at that time, you are only interested in broad parameters and so on. At that time, only steady state is used. And but when you want to do any dynamic analysis, dynamic simulator is used. So based on your objective of what you are looking at it, you have to select the particular tool. And again, in steady state also, what tool I should use. For example, if you use Aspen has got so much of library in it. It's a huge ocean. What module you should use it, and then what thermodynamics option should be used. It itself is a big learning. You need to get familiar with that and try out various things. And there are online guidances, help manuals available in all these tools. And based on the context and based on for example, the thermodynamics will be determined by the components that are involved in the system. Suppose you are using any chemical component or you are using hydrocarbon. Based on the thermodynamic selection or unit selection will be made. So the tool selection, option selection will depend on the context, and definitely it's part of the learning that you have to go through during the tool learning.
Yes, sir. There's a last question from Abdul Rahman, who's from Satyabama. So what are the software used for this simulation process?
Software, see, mostly still it's all in Visual C++ language, but there are others who are also doing some time in .NET and so on. But primarily we are using Visual C++. In fact, many companies I have seen, they are using Visual C++ as a basic code. But one thing is today, the coding requirement is also coming down drastically. Like IT industry, the softwares are all, as you would have already seen, Aspen, ISIS, people who have used it. You don't need much coding. You already available, drag and drop. You can configure your plant, and the libraries are already developed, available. You enter your data, you can do simulation. But so without doing coding, you can also do simulation. Only one thing is, if you come across new equipment, if you come across new process, that time only this coding requirement is there. Otherwise, without coding, most of the jobs can be done today. So that's the advantage also. So you don't need too much of coding knowledge or expertise in that. Without that, you can do a lot of job. But if you have this coding knowledge, you will add to your applications. You can do more things. That's all.
Thank you, sir. Is there any more further queries? Is there
Sir, I have a small doubt.
Yeah.
Yes.
Sir, why is the softwares like this Pro Simulator, Aspen HISIS and all, they are not a part of the syllabus, but this ChemCAD and all is there in the syllabus. So why it's very important for a chemical engineer to know these softwares, learn this, but why it is not included in the syllabus? And I'm
See, one cannot, whether you use ChemCAD, Aspen or whatever, there are so many. If you just know one, it's enough. No point in having all the software knowledge, because the tools are easy to switch from one. If you know the concept, if I know one of them, you can always learn other very, very easily. College cannot teach you everything. As long as you get them exposure to it, first the college focus is to teach you fundamental very well. That is our main. Then simulation will come during the 3rd or 4th year at that time. So it's enough if you get exposed to one software. It's not possible they don't have time, and they don't have so much overload is there already, So naturally, if you learn one, it's enough. Based on their, cost or whatever consideration, they would have put one software in their college. Sometime they would have used Aspen. Sometimes some colleges will use DWSIM. Some people have bought ChemCAD. I have seen different people use different software. Doesn't matter. Whatever be the software, if you're able to learn one tool, you can definitely easily learn any other tool without much of an issue.
Sir, if I learn ChemCAD, will I have an idea of learning the other softwares?
See, definitely ChemCAD is a steady state simulation. ChemCAD, if you learn, Aspen, ISIS, all this we can easily use without any problem. But of course, dynamic simulator will require more different kind of training again. Like Pro Simulator is a dynamic simulation tool. It requires some more training. But definitely the basic ChemCAD, if you're used, you would be having advantage. So you will be able to pick up very easily. That's all I will say.
Thank you.
Yes, sir. Thank you, Shetal. There is one more question from a chat box, sir. Divakar has asked, what are the difference between mathematical modeling, process simulation, and computational dynamics?
Actually, mathematical model simulation, they are get mixed up. Both are same only. I mean, we keep on interchanging each other. Basically, what happen, any equipment, you have to write mathematical equations governing that equipment. That is called mathematical model. Okay, and you make the model to a software. It's called simulation. So basically, equation, we convert it as a software, it becomes simulation. That's all. So these two are interchangeably used. Don't bother about exact definition of it, whether they use mathematical model or simulation, or now there is another terminology which is being used, digital twin. People are using in the this Internet of Things and all that. They are using another term called digital twin. All these are basically same. Underlying principles are same. It's a software ultimately derived out of the equation that you write of a particular equipment or a system. So terminologies may differ, meaning the same thing, concept.
Yes, sir. So what you said is perfectly correct. Yeah. Yes, sir.
I have one doubt, sir.
Yes.
Sir, Raman,
Arun, can you drop in the chat box? I think your network is poor. Arun, I think your voice, we could not able to hear it. Can you drop in chat box? Yes, sir. I think, thank you so much, sir. Maybe we will wait for him. But definitely, I think what you said is perfectly right. Because like even we need the basics to be always learned. And chemical engineers always study so many mathematics paper. We may not know like why we are studying these many mathematics paper other than other departments are doing it. But now the simulation, CFD and mathematical modeling, everything correlates. So definitely, I think the students can link about that. Then only they can able to find the mathematics paper also is very easy. Otherwise, I think they could not able to come out it. So maybe Arun, okay. Okay, maybe okay, fine.
Of
So,
course,
Arun,
you can contact me anytime through email or things like
yes,
that.
sir.
I definitely will be happy to
Definitely, sir. I
support.
think, can you just,
Yeah.
okay, drop your mail ID in the chat box, or I'll just
I'll
post
do
it.
that. Yeah, I'll just do that. vraman@siminfosystems.com.
Yes, sir, definitely. So I think it's almost like we have crossed 1.5 hours. So definitely, sir, thank you so much. I think even I should thank Raman sir as well as Raghuram sir. So I was like very much like we have Raghuram sir in a very close compact where we had a 1-day session in our Anna University AC Tech last year. Sir could able to spend his complete day and for the chemical engineering student. I think our SIMS info system is doing a lots of contributions for the students community because they are the next pillar of our country and they should know what is really happening in the world through this advanced technique. So I thank our director and CEO of Siminfo System, Raman sir, who could able to join this evening. I think maybe Chennai is also downpouring, so with heavy rain.
Yes, sir.
But
Thanks to it, sir. Thanks.
still, I think
We are
sir could
happy
be able
about
to
it.
join without any like network issue. So also I should thank our Raghuraman sir who could able to bring our Raman sir for this session because we have not seen such a session like from the industry point of view. Because industry people can give up only like what we learned, especially on the distillation or what the problem facing. But this is one very important advanced technique we needed from the experts like you, sir. So the IEA TVLC like wishes for both of you for joining in this session and gives us lots of valuable for our students. So definitely, I think definitely, I think we will continue with the same in the near days, also coming up days, and we will see how like we can able to nurture our students in the areas of this dynamic software. Thank you so much, sir.
Thank you. It's a great pleasure for us. Thank you very much, sir.
Yes, sir. Thank you, sir. Thank you. I think Raghuram sir, you have to unmute. I think, sir.
Sir, you have to unmute. Raghuram?
Yeah.
Okay.
So I thank young scientists, dynamic scientists like Mr. Gokul, to making this the platform, bringing the next generation Z, to the industry for industry. When 4.0, what we are into it. So I was really appreciate your great efforts in bridging this generation Z to 4.0 industry, what we are into. So we thank you a lot, and we looking forward for many opportunities, not to elevate this, the new generation chemical engineers, and to enrich them, and we'll prepare them for the need of this digitalized processing, chemical processing world, sir. So I thank you once again for making this, the meeting and arrangements, your coordinated efforts.
Yes, sir, definitely, sir. I think by your session from IICH in the last, maybe in the December, I think now IICH is going to have one MOU with, I think it might be over, I feel, from headquarters. So definitely that is also going to give a lots of a potential movement for the students community with IICH and the SIMS info system, so that a word of this kind of a dynamic software should spread it among the students community, and then they can also become a real simulator engineer, how you are all become. So with this word, I think I thank both of you from SIMS info system. And also, I think after online, I think this is a Corona period. Still, maybe it may take another 2-3 months. Once vaccine comes, we can even meet in the offline, and we can have some more like a valuable additions for the students community, and also with some more industries where we are being linked up for the next level of the work movements. So thank you so much, sir, Raman sir and Raghuram sir, for joining this today evening and making us so happy. Also, the student community. Thank you, sir.
Thank you very much.
Thank you.
And one more, the final information I want to share with you, as I discussed with you. See, I want to bring this, for our next generation chemical engineers, the basket of opportunities post-COVID. That's what I discussed with you. Since this is a more focus on technical section, so I will be, for next session, I'll be dedicated for this, opportunities for our new generation chemical engineers, where I can bring the global opportunities. So I can bring that complete the limelight of the opportunities available for our chemical engineers. So in the next session, that will be an elaborated way. They will be get more confidence and they will be appreciated.